Well, hello, everyone. I think we need to get started. Bruce Balick from the university was here a couple months ago and gave a wonderful talk. It turns out there's more going on in the universe than you can cover in an hour. So he's back. So we're looking forward to hearing what follows. Thanks.
And what a nice brief introduction. What a nice brief introduction. Time is so valuable. He's great. And it's a pleasure to be back. Last time we ran way over time because there were so many fabulous questions. And the last thing I want to do is to stifle a good question. The best audience is a third grade audience because nothing stifles them. At your age, people don't want to raise their hand out of, I think, embarrassment, just in case they ask a stupid question. As you'll see in this talk, it's hard not to ask a stupid question. And partly that's because of how little we actually know for sure. But let me put up a slide that you've seen before. That one. This stuff is very abstract. The origin of the universe, people imagine it to be like a movie. There's a big bang at the beginning and stuff floats out and coagulates into galaxies. And that's kind of the story. But as if you remember last time, in addition to all of that, we went over some what appear to be conundrums. For example, the universe is expanding, and let's move right into that. The universe is expanding. Hubble found this. I won't go into the details because I did it last time. But Hubble found that by observing galaxies, which are like little fireflies that fill the universe and make it possible to see where space is transparent. You can't look at it. I mean, you look through it, you don't look at it. So the galaxies are little tracers that tell you what space is doing. Galaxies were formed, I'll come back to this a little bit later, but they were formed essentially in an instant after the Big Bang itself. By that I mean 100 million years. That doesn't sound like an instant to you, but in cosmic time, that's nothing. And it took that long for the universe to settle down so that stars can form. The stars in these galaxies emit the light that we can see. If there aren't stars, there's no light to look at. So I might just add that the James Webb Telescope was designed to look at the first stars. They're very far away, so it takes a big telescope. And as Hubble found, the universe is expanding in such a way that distant things move away from us much faster than close things do. That's portrayed here. We're at this point, and the nearby galaxies are just only slowly drifting away from us. The distant ones are really moving. And the galaxies that were the first to form are so far away that they're moving away very fast. They're moving, their spectra, the spectra of the starlight in these distant galaxies is shifted out of the visible spectrum. I mean, the stars in these galaxies aren't that much different from the sun. They emit a lot of light. But the Doppler shift shifts their light into the infrared part of the spectrum, and Webb was designed to work on that. Is there anybody who doesn't know what a Doppler shift is? It's not important for this talk, but you've all heard it. If you've stood along a train track when a train is coming, not on the tracks, just off to the side a little bit, the pitch of the train changes as the train goes by. It goes from to as it recedes. And that's the Doppler shift. And everything is moving away from us, as I explained last time. So the shift is all of the and increasingly until you can't see the light in the visible part of the spectrum anymore. But it's there. And Hubble couldn't see far enough in his time, 1929, to notice that the light was outside the visible spectrum, but we certainly know that now. So in short, what he found is shown in this cartoon here. Whoops. Over the course of time, galaxies are moving apart from one another. And their light is Doppler shifted. What's important in this is that the spacing between any pair of galaxies increases over time. And that's because space is expanding. The galaxies are sort of caught in a nest of space, and they go where space takes them. And so this expansion is an expansion of space as marked by the fireflies of galaxies. Okay? And Hubble's observation was never expected, ever expected. Early pictures of the universe just had it as sitting there doing nothing. No expansion, no contraction. When Einstein heard of Hubble's observations, which came much later, he had finished the general theory of relativity. One of the things in his theory that he showed was that space, if it's static, it can't stay that way. It either has to expand or move outward. It's like a marble up on top of the mountain. It can't sit there. It's got to roll one way or the other. This expansion of space was not what Einstein expected, what anybody expected, because as far as we can tell by looking out there, the universe is filled with stars, and stars are made of mass. And with mass, you get gravity. And gravity is an attractive, not a repulsive force. And so it was felt that if the universe is doing anything, it would certainly be collapsing. So Hubble's results that the universe is expanding came as a big surprise. Anyway, the image to keep in mind is this one up here of a balloon with galaxies glued to its surface. The balloon expands and the galaxies go along because they have to. Now, on top of that, about 20 years ago, we found that the universe is not only expanding, but the rate of that expansion is increasing over time. That's about the last thing we expected to find, but there it is. And it's an observation. You don't get to argue with it. The expansion of the universe is increasing over the course of time. And we'll come back to that, because that expansion is what determines our future. I'll show you why. But the Hubble's observations and the acceleration rule out the Chicken Little theory, which is a pretty good theory. I mean, go back 100 years, everybody's expecting that gravity will collapse the universe. So Chicken Little made sense. What we see is what doesn't make sense. And that's why you have to keep your mind wide open, because what you see is not what you expect. We found out, there's not time to review this, but if you ask about the energy budget of the universe, in the special theory of relativity, Einstein showed that mass and energy are equivalent, E equals mc squared. So you can look at the mass in the universe, which represents an energy, and the matter that we can observe, the matter that gives rise to light that we can see in a telescope, is this sliver of the energy budget of the universe. Almost nothing. Now, Vera Rubin and her colleagues, this is all in my lifetime, found that galaxies are rotating too fast. That is, there must be additional gravitational forces that bind a galaxy together, because it's really simple physics. Galaxies go around and around like this, And at the speeds that we see in galaxies, the stars should have been flung out, and they weren't. So there's a force which is keeping the stars in those rotating galaxies, including ours, down to the galaxy. And that's this sliver of it here. It's dark matter. You can ask what dark matter is, but you won't get an answer because nobody knows. There are a whole lot of, it might be this, and this, and people are doing very active experiments. One of the most hopeful is up the street here at UW. But we don't know what it is. And it was never predicted. There's nothing that predicts it. But the big slice of this pie is right here. Dark energy. When you look, so as I said, the universe is expanding. That expansion is accelerating. And that takes energy. And the amount of energy needed to account for the expansion of the universe is it's called dark energy, and we have no clue what it is. So keep your mind wide open, and I would just love to see a resolution of this in my lifetime, but I don't think it's going to happen. Whoops. I can't put my finger on. All right, let's go back, and we're not going to move into the theory of the Big Bang. It's a theory that tries to account for the strange things that we see. Okay, now, first of all, Hubble's observations tell us that things are flying apart. So if you take a movie of the universe, this expansion, these things moving apart, and you run it backwards, everything crunches, and that would be the Big Bang. The Big Bang was a name coined by Fred Hubble, who didn't believe a word of it. In his time, Fred Hoyle was convinced that matter. So, let's not go into that. The universe has a beginning. That's when all these galaxies come back together, and you can imagine that as an explosion, but that's not. I mean, that's a little simplistic. Explosions are really messy. This is a very orderly expansion of the universe. So off it goes. Last time we talked about why there was a Big Bang, and we can't answer that question. Most of the questions that we went through last time don't have answers. This is one of them. You can't ask what came before the Big Bang, because the only way we could ever know is if signals propagate from before the beginning of time to a telescope where we can observe them. Right? And the only signals that might do that are light, and when we look out into space, we're looking into earlier and earlier times. I mean, when we look at the sun, the light we see is 8 minutes old. When we look at the nearest galaxy, anything like ours, the light we see is 2 million years old. When we look at these very distant galaxies, their light is 13.8 billion years old. And there's no way, since the universe is only 13.8 billion years old, there's no way to see anything beyond the 13.8 billion light years away. So we don't have we have plenty of theories that describe what might have happened, but we don't have any that are testable. So here's a summary of the Big Bang Theory. It's a very good one. There's nothing. Who knows, or whatever it is, we'll never know what it was. And then out of nowhere comes this expansion of space, which continues to this day and is getting faster and faster and faster over time. Why was there a Big Bang? The theory does not provide even a clue to the origin of time. Now, the Big Bang Theory is a model, and models are made to put pieces together, but there's so much that we don't know, and in principle cannot know, that the Big Bang Theory will remain an incomplete theory I think, forever. Every once in a while, we fit a new piece into the puzzle. But more often than that, we get a piece that doesn't fit, but it has to. For example, Hubble's observation of the expansion of the universe, that was never expected. And there's still no explanation for it. And the acceleration of that expansion is another puzzle piece that just popped out of nowhere, and we don't quite know what to do with it. That's what makes this whole topic so bloody fascinating. It's frustrating that there are things that we will never know, right? And so we won't get to the bottom of this, at least not in my lifetime. But we're finding the pieces that we get, and when we finally figure out a way to fit them into the puzzle, they reveal an amazing, amazing universe. And that's why your mind has to be open. Very quickly, what happened after the Big Bang? So at the time of the Big Bang, there was a heck of a lot of energy in the universe. We don't know where it came from, but the universe was incredibly hot. So hot that you couldn't yet have atoms, because particles, even if they have opposite charge, don't have enough charge to hold themselves together in the face of this unbelievable amount of heat. I'll show you a graph a little bit later. So at the dawn of time, there's a lot of heat. A lot of things happen. We'll quickly go through those. They can't happen now because there was so much. There's much more energy back then than we can produce in a laboratory. We can develop physical models about what might have happened at those temperatures, but we can't reproduce this in the lab. We'll look at that. The next big, so stars don't form for a long time to come. The next big event is that the universe becomes transparent. The universe at first was very, in addition to being hot, it was really, really dense. And light has a hard time propagating through dense objects. So there's a wall back there. I can see what's on the surface of it. It looks like wood. From our vantage point, as we look back into time, we hit a wall known as the cosmic microwave background. And we see a little bit of structure in that background, but we can't look. That wall, space becomes transparent at 380,000 years. And we can't look to earlier times because the universe is opaque. None of the light created at earlier times is able to break free and come our way. But we can study the patterns on that wall, just as I can see patterns that look like wood. And on a stormy day, you can walk outside and you can look at these clouds that look like they're roiling and boiling. You can't see what's happening above them, but you can tell from the structure that you do see what's likely to be going on. And so a lot of what we know about the early universe comes from measuring the ripples of irregularities on that wall back there and trying to figure out how they got there. It's a very, very challenging problem. But we do it, and the Big Bang Theory consists basically of the conclusions that we reach from doing that. And then the next event is the present. So once the universe becomes transparent, very shortly after that, matter begins to puddle itself up, and eventually it puddles itself into proto-clusters of galaxies. And those, they're still transparent. Those proto-clusters of galaxies fragment thanks to gravity. They fragment into smaller puddles, which eventually become galaxies. And then within the galaxies, the fragmentation continues until finally you get enough density to make a luminous star. So that's a major event in the history of the universe, and it's what the Webb telescope was designed to explore. And I don't have time today to talk about what Webb is finding. I will say, however, it's finding lots and lots of puzzles, not things like Hubble's law, things that we absolutely cannot explain, but we're finding that given our best theories of how galaxies form, the data from Webb tell us that we're wrong. The galaxies formed much earlier than we ever expected, and eventually we'll figure out why. But the reason you spend all that money on a telescope like Hubble or Webb is to be surprised, is to get information that you never expected to get, and that's how learning proceeds forward. Now, eventually the universe cools down to a point where gravity can pull things together to make stuff. And this is this is the outcome that you're looking at here. It's a computer simulation. It's not for real. But orange light is starlight, right? And the earliest galaxies were really ragged. We can see that in the images from Hubble and Webb. And then it appears that dark matter also began to condense, but not to make galaxies. It made filaments. And we still don't understand. We don't understand dark matter, so it's very difficult to understand why it made filaments. But we can simulate that by making assumptions about the nature of dark matter, and then making movies. And the movie that you see here, the only force at work is gravity. And we've known about gravity since Isaac Newton and Einstein. There's nothing very sophisticated about understanding the structure of the universe. It's, in terms of physics, very simple and straightforward. But what you get at the end depends on what you start with. And it's what you start with, which is the end of the rainbow. The pot of gold is the end of the rainbow. And we're, thanks to Webb especially, we're beginning to see what happened. All right, now we're going to start over again. We're going to tackle this question of what was around before the beginning. The universe, as far as we know, at the time it was born, it's infinite in size. Infinite in size. Now your head has to be open. What does that mean? Well, for one thing, it means that there's no center to the universe. No center. In infinite space, in an infinite space, you observe what's around you, and what you see is what everybody everywhere else would also see. And so there's no center. That's a hard one to process. What came before? I mean, and we don't know, and we don't even know that the laws of physics that we understand for our current universe even applied before the beginning. But if we make that assumption that we know the processing, we may not know the details, but we know the processing, that's physics, we can make up stories about what came before. And I'm stymied here. I don't know how to put into words the uncertainty principle and what it meant at the beginning of time. It just, the uncertainty principle basically takes you to a visual model that looks like the one at the bottom. This is a two-dimensional universe with three-dimensional structure. Our universe would have been three-dimensional with a fourth dimension that you need to describe the structure. That's why the general theory of relativity is a four-dimensional theory. And in quantum mechanics, you get these strange occurrences. They might be brief, they might not be brief, but somewhere in this foam, a blob of the stuff that can hold itself together forms, and that's a universe. And there can be many, many universes that made out of this primordial stuff in an infinite universe. We're in one of the surviving universes. There may very well be others, and there's no reason to expect that in those other universes the laws of physics are at all familiar to us. They could be 11-dimensional spaces. They might be matter-free, or if they have particles, those particles might have nothing in common with the particles that we know about now. I hope you're getting the sense of how little we really know. But we do know there's a beginning. Hubble's law forces that on us. This expansion, if you play the movie backwards, everything comes together and begins to move apart when you restart the movie. That universe is very compressed. And when you compress a universe, it gets really, really hot. Extremely hot. The physics we know is very difficult to test at the temperatures that we expected for the early universe. But we do know what happens afterward, and we can kind of work. You can take the clock apart and see how it works. Here again, I want to emphasize the universe is infinite, which means it always has been. You can't take something which is infinite now and make it finite earlier or later. It's this big infinite applied at the very beginning, right at the outset, and everything that we see as we look out with Webb is characteristic of what everybody would have seen. The important point here is that if you look at the energy budget of the universe, and it's that energy budget that really determines the nature of the universe. At first, all the energy in the universe was in the form of, almost always, in the form of light. Matter as we know it was, in terms of particles, protons and electrons, there is still many seconds into the future, which is a long, long time. Here's a graph. If you're good at reading graphs, this gives you an idea of the temperature. The universe expands, and expanding things cool down, and they do it in proportional to the size of the change in the volume. So let me go back here. Here's the universe today. We measure that age to an amazing precision, and we can do it from looking at the motions of the galaxies. So we know how space expanded, and we know then what the temperature of the universe did as it expanded. It just came down. Now up here, the energy in the universe is mostly in the form of these little light particles known as photons, and they had a lot of energy. They don't anymore because the expansion of the universe has Doppler shifted their energy and to something which is much cooler. But the typical photon back then had as much energy as that one little light particle had as much energy as the Cooley Dam generates. The effect, so energy and mass are interchangeable, and these photons had so much energy that they were on the verge of becoming their own black holes, which is a startling thing to think about. I can't do it. Now, expansion dilated the energy density of the photons. And so the energy in light began to drop very quickly. And there are other kinds of energy which show up later that overtake radiation, and we'll come to that near the end of the talk. But because of the expansion of the universe, that is, because there's no way to hop off of this line. If you take this line, this one here, move it into the future, you can bet that it's going to be clear, the universe is transparent, and colder. We'll talk about at the end if there's any time. I'm not doing well. So, let's talk about the so-called Planck era. the universe has some sort of things in it, but for the first brief instant of time, these things are further apart than light can travel through the age of the universe. Which means that these things, whatever they might have been, were not being affected by any other things because light, which transmits information about forces, didn't have time to get from one place to another. So the early universe would have looked like individual splashes, right? And until the waves representing light, until they overlap, nothing knows about anything else. A very strange time. But it ended very quickly. So as time went on, even though the universe is expanding, as time went on, these little ripples in the sea began to overrun one another, and things became aware of other things, which meant that forces could make them into fashion them into new forms of matter or energy. I don't want to, because I'm running a little late, I'm going to try to speed up here. But it's the second major era in the history of the universe is when these rings begin to overlap and things realize that there are other things, that is, forces from other places begin to do work, change the nature of the universe. The third era is one that I didn't mention before, and we're not going to spend a lot of time on it. But and we don't even know that it happened for sure. But without something like this, we can't explain what we see today. Here's time. We're talking about 10 to the minus 35th of a second, which is almost nothing at all. It's hard to think of an instant that short. But it appears, from what we see today, that the universe underwent an amazing expansion, an expansion many times faster than the speed of light. Many, many times faster than the speed of light. So, we'll take a look at that. I can't explain it except through analogies, but separations before inflation, separations the width of a proton, that's this tiny fraction of a kilometer, separations instantly grew to by a factor of 10 to the 40th or so, which means that protons which might have somehow been near one another disappear. They move apart at much greater than the speed of light. Now, last time there was a question, you can't move faster than the speed of light. That's true for things that are in a space. Space itself, however, has no constraint like that. And so space could have expanded far faster than the speed of light, and suddenly things that are near one another disappear from each other. There's no time for light to get from one to the other. And so the universe separates into small puddles, which are still connectable using light in this brief instant. So the analogy I'm going to use here is that think of the early Earth, but this is going to be an expanding Earth. So here are the original cultures to form on the surface of the Earth. They're separated, but there's a runner can get from one nearby culture to another one. But then the Earth expands faster than anybody can run. And so each one of these little spots here becomes a culture that is now separated forever from all the other ones. I know this is difficult. So that's the period of inflation. And when it ends, the continents have all separated the little puddles that represented a single culture still remain, but they've lost all contact with each of the other puddles. It is such a strange thing. It is so difficult to visualize this. That's our problem. Whoops. So what begin as, I call them bubbles, I should have called them puddles. The ground on which those lakes are found has expanded so fast that if you're in one of these puddles, you can't see the other ones anymore. And so the universe in which you find yourself living is a very homogeneous one because it's all part of the same puddle originally. Okay. We're going to slow down now. I mean, we're going to talk about things that might actually begin to make some sense. Particles form out of this light energy. It's still too hot for protons, electrons, and familiar particles to stay together. That is, if they form, the heat of radiation around them will split them up into more elementary particles. So it's these super elementary particles which form at first from the energy of light, and they make new kinds of particles, and over the course of time you get to what are called quarks, which are particles, and those quarks, various combinations of them shown here, begin to make familiar particles. Now, we're within the first billionth of a second. I mean, time has just barely started. But it takes a universe which cools down to the point where the energy of light doesn't destroy anything inside of them. And so protons and neutrons and electrons are formed out of these quarks. They're basically forming from these photons of light converging on one another. So it takes two photons to make this work because of selection rules in quantum mechanics, which I don't have time to go into here. But two photons can meet in space and form a pair of particles, an ordinary particle and its anti-version, an electron and an anti-electron. Or if there's more energy, 1,000 times more energy, you can form a proton and an anti-proton, or a neutron and an anti-neutron. All these things are just forming in a universe which is filled with these energetic photons, and suddenly there are particles that are familiar to us. But it's still so hot that collisions between an electron and something else can split these particles back into photons again. So you have this universe which is continuously making and annihilating the particles that are formed within it. It's a fascinating idea. So here's this jumble of stuff, particles, photons. The photons are the blue things, and all of them are embedded in a universe which is expanding. And because it's expanding, the universe is cooling down over the course of time. And that sets a direction for matter which is irreversible. Here's what I mean. When the universe gets cool enough, an electron and an anti-electron can meet and annihilate and make photons, new photons. But the photons rattling around the universe, because of the Doppler shift, or the decrease in temperature, they no longer have enough energy to come together and make a particle and anti-particle pair. So the annihilation of matter and antimatter keeps going until there's nothing, there are no pairs left. Right, and so a big question in physics has been, what are we doing here? If all the particles in the universe and their antiparticle siblings annihilated, there shouldn't be any matter. Well, we're here, so that's not the right answer. It appears, for reasons we're just now beginning to understand, that there was a residue of what we call matter. The antimatter in the universe all was annihilated, leaving behind 1 part in a billion normal matter. And that's where we come from. So there's there's an asymmetry somewhere in the nature of matter, which leads to this small residue. And that's a whole different lecture and would have to be given to you by Bill back there, who understands this stuff. All right, now the universe has gone through this amazing set of transformations, just violent transformations. And we are just arriving at 1 second after the Big Bang. There still aren't any stars. There still aren't any planets. All there is heat and this sea of particles, the residue particles rattling around in the universe. But the universe continues to grow and cool down. And so these particles can get together and make things. They can make, and they do make, compound nuclei. Not many of them, but there are protons and neutrons around. And then, until about a minute, it's too hot in the universe for these things to come together and make a stable nucleus. If they make a stable nucleus, the heat in the universe breaks it back apart again. But after about a minute, the universe has cooled down to a few 100 million degrees, which is still pretty hot. And now the compound nuclei that are being formed from neutrons and protons survive. But then the universe continues to cool, and after a few more minutes, this process stops because the particles that make the compound nuclei no longer have the energy to do it. So what you get is you get a lot of helium nuclei. Hydrogen nuclei. That's a simple proton. And you get a little bit of helium, which is 2 protons and 2 neutrons, and not much of anything else. Okay? So we're now at a minute into the history of the universe, and nuclei that have names that are familiar to us, nuclei that make up everything that we know of, at least the very simple ones, have formed. But as it turns out, if you try to form anything more complicated than helium, there's still enough heat in the universe to destroy it. There's no gold, there's no iron, there's no oxygen, there's nothing in the periodic table except for a tiny little bit of things that are up near hydrogen and helium in the periodic table. But they're insignificant. If you're wearing a pair of glasses, that metal is forged later in the history of the universe, not at the beginning. Right? So metal, gold, all those things occur later, and they're made in stars, as it turns out. So time goes up in this cartoon here. There's this hot universe consisting of protons, a few helium nuclei, a bunch of electrons, and after 380,000 years, it's finally cold enough for the electrons to settle into orbits around the nuclei that fill space. And so, for the first time, atoms form. Down here, the free electrons and all the elements, the nuclei, are known as ions. But after the universe cools to below 3,000 degrees, which is roughly the temperature of the sun, atoms begin to form. The electrons hop onto orbit levels. And what had been a completely opaque universe up until then suddenly becomes transparent because light can travel through a sea of atoms, which are neutral. It can't travel through a plasma, which is where everything is charged. In a plasma, if you take one of these little photons of light, it'll start to bounce around just as light does inside of a fog. And then suddenly, when the universe cools to 3,000 degrees, the fog disappears. And for the first time, we can see through long distances in space. So important to have a transparent universe if you're an astronomer. And this is the structure of space at that time. These are satellite observations of that opaque wall back there. And there's structure on it, not a lot of structure. What you see here, the little yellow things, are about 100,000th brighter than the blue material, but still there's structure. And this structure got here for some reason or another. Whoops, I gotta keep my hands off it. How this structure got here can be understood with the laws of physics, we think, as we know them now. And so this structure in the early universe, the orange regions are slightly denser than the blue regions. That means slightly hotter than the blue regions. There's structure there. And that structure has a story to tell, which we're learning how to read. And we're learning how to read it not at this stage, but later on when stars form using the James Webb Telescope. And that telescope really is giving us a view of a structured universe, earliest phases of a highly structured universe. Okay, the talk is we've just about reached the present, because after galaxies and stars form, nothing much changes. Everything is familiar. I mean, if you're born on a brand new planet, then that planet is not familiar. But the grand structure of space doesn't evolve much after 380,000 years, other than the expansion continues and the temperature continues to drop. So here's a summary of what has happened. This green box covers the time from opaqueness to the present. And atoms, more complex atoms are formed in stars, they float around in space, they make dust clouds, the dust clouds settle into new stars. This is a story that you'll learn about in Astronomy 101. Back in here, because space is opaque, it's very difficult for us to see what happened. We can only infer what happened earlier by looking at that wall back there and the structure in it. I'm going to move ahead here. I'm going to skip this one. All right, so this is the summary. We're going to look into the future very briefly. There's still a little bit of time. But here's now in this expanding, accelerating universe. Right, and this acceleration means that the separations of things will continue to not only increase, but increase faster and faster and faster over the course of time. If nothing else, this expansion of the universe is going to leave us very far from other things. The sky that we look up and see now will be a much emptier sky, a much colder sky, right? And as the distances between galaxies increase, they fade and fade. They're still there, but they fade and fade. And so the sky becomes darker and darker. But there's one additional thing here. Because the acceleration of space, because of that, the separations of particles can increase beyond the speed of light. So those very distant objects begin to move away from us faster than the speed of light, which means there's no way for their light to get to them, to us. And so in this strange future universe, the distant galaxies begin to blink out one after the other, starting with the most distant ones, and over the course of time, the era of darkness kind of comes in our direction. It's going to keep getting colder. I mean, it's going to be a lonely universe compared to what we have now. And that's nothing compared to what we're going to have in the distant future. So we can predict darker, colder, and less dense. However, systems like the Milky Way, which are held together by gravity, they're not going to fall apart. The forces of gravity are much, much stronger than this expansion of the universe. So galaxies won't be ripped apart. It's just the separations between galaxies which will increase rapidly over the course of time. Now, because the density goes down, the availability of new material to make new galaxies goes away. And within galaxies, galaxies are using up their supply of mass to make new stars. So within galaxies, over the course of time, the star formation rate will go down and down. It has already gone down. The Milky Way, when it was born, was just a lot of gas to make plenty of stars. We've used up over half of that gas, which is locked up in the corpses of the stars now. And that's a process which will continue as long as star formation does. So star formation will slow down and eventually, a long time from now, come to an end. What we're left with, the corpses of stars, are these things called white dwarfs. Right? They have the mass of a star, but all that mass is contained within a volume which is about the size of a mountain, like Mount Rainier. So gravity has done all that. In some cases where there's enough mass, gravity will take a white dwarf and shrink it into a black hole. So the final products of star formations are a bunch of white dwarf stars and black holes, and they're not going to make anything new. They're far apart. Gravity still binds the universe, the galaxy together, but the gas out of which stars are made, that's all depleted at this point. The sun, when it reaches, I'm going to shift topics here very briefly. We can talk about how stars evolved. We can talk about how the sun evolved. It began as a wad of dust and gas 5 billion years ago. Right? That's the age of the planets and the age of the sun. The sun will continue to evolve, and it will burn up the fuel it has on its way to becoming a white dwarf. But along that path, the future sun will swell up to become a red giant. And when that happens, the orbit of the Earth is likely to be very close to the limb of the sun. The limb of the sun. So you can just imagine this Earth going around through the surface of the sun. You look around, it's really hot, right? Because the sun is hot. The temperature outside will be about 3,000 degrees all the time. The oceans will disappear, evaporate. And the rocks that are there will work their way towards porcelain. And then after that, what's left of the white dwarf at the very center, at the red giant, that becomes this white dwarf. So here's my phone is ringing. I hope you can't hear it. I'm going to turn it off. Here's a graph that I swiped from a BBC story in which time increases as you go down. And major events in the future of the universe are highlighted here. In 100 million years, the Earth, I'm just going to hit the highlights because there's no time for questions if I don't. Sorry, my phone continues to. It's in my hearing aids. It annoys me. It doesn't annoy you. So there's this thing that it's like a scroll of the future, like a Torah, and I've torn it up into pieces and picked some of the interesting epics out of it. In 100 million years, let's see. The star Betelgeuse in the shoulder of Orion that you can go out and see this evening is likely to explode as a supernova. When you get far enough into the future, other galaxies that are in the same cluster of galaxies as we're in, they're all kind of swimming around, held together by gravity. And every so often they collide. And the beautiful galaxy, the Andromeda Galaxy, which is our nearest counterpart, will collide with the Milky Way in 5 billion years or thereabout. Now, galaxies like the Milky Way, or M31, and the Andromeda Galaxy, have stars, and the separations between the stars are really huge. So when this merger happens, the stars will go right through without touching each other. But all the gas and the dust in the Milky Way and M31 will be stripped away as a result of this interaction. And that'll really bring an end to star formation. Here we are looking at 1 million to 100 million years. The word men appears here. This slide is old enough that was excusable in the old days. Humanity is likely to become extinct in roughly 5 billion years, which is the result of the sun swelling up and engulfing the earth. Right, we fry. So the biblical vision of hell seems to be right in our future, but it's a long time away, and you don't have to sell your stocks yet. This is 100 million to 10 billion years into the future. The universe is about 13 billion years old, so this is one cosmic time into the future that we're looking at the bottom here. And the sun has already been a white dwarf. White dwarfs can't produce any new energy, so they cool down and become black. The sun's hydrogen is exhausted. The sun's radius hits a maximum here in 7 billion years. The sun becomes a black dwarf here in the timeline. It's not a very cheerful future, at least if you like what you have now. Even longer into the future than that, this acceleration of space, the fact that things begin to move away from us faster than the speed of light. The distant objects do that first. The nearby objects take a long time. And all the galaxies that we can see up in the sky at night. Whoops, sorry. I should be using this thing. All the galaxies that we see in the sky at night, the distant ones will all go away. So we won't be seeing these. These won't be our friends for much longer. If for no other reason, star formation is going to run out in all these galaxies. But also the expansion of space is going to blacken them. We're out of time. So this is the last slide. What's left? 10 to the 39th years, which is 10 to the 29th times longer than the age of the current universe. This is the far distant future. What do we think will happen? The white dwarfs, they become black dwarfs. And we think the quantum mechanical effects are going to destroy what they're made out of. And so they'll vanish. move forward to 10 to the 100th years, the universe has expanded. Never mind. I want to leave time here. So, that's it. Sorry, I screeched to an end here. That's the way this talk sometimes goes. I would be thrilled to entertain questions from people who are still awake. Does that mic work? Does your mic work?
I'm Gordon Oriens, member of the Science Committee. I'm a simple-minded ecologist, but I think I'm capable of moving the microphone around. So we're open for questions for Dr. Balick.
How do you explain consciousness in the universe,
Oh, jeez.
such as ESP?
Talk to a psychiatrist, not to an astronomer. We don't deal with life. Life is too complicated. We'll never understand it as well as we understand cosmology.
If the universe is expanding, where is it expanding to?
Well, remember, the universe is infinite, so when a universe expands, it just gets bigger and bigger. There's no edge to it, so it just keeps on going, getting bigger, but infinite is infinite. That's a lousy answer to your question, isn't it?
You talk about this as if there's nothing that's going to happen in the future that we don't predict.
Yeah, well, that's
So-
crazy. I can't see who asked that question. Oh, okay.
Yeah, I'm just saying, you're assuming that everything is going to continue on this pattern that you've discovered in terms of the way the universe
Yeah.
is expanding. But couldn't there's something intervene that we're not expecting?
The first thing that will intervene is new knowledge, which
Yes.
will rattle our cage and make all of this look sort of obsolete. But if we assume that the laws that we understand continue to go, then the fate of the universe is well determined. But, revolutions in science come at least once a century.
I understood that in the cosmic foam there could be little bubbles that
Yeah.
might make alternate universes. But it
Yes.
seemed to me when you talked about the bubble or the puddles that could no longer see each other,
Yeah.
that might mean that the universe we're observing is one of multiple universes that happened
No,
after the Big Bang.
It's one of multiple puddles that we can observe. The other puddles are out there right now, and they could be quite different from ours, but we'll never be able to see them.
Right.
Because they're moving away from us faster than the speed of
Okay.
light. Yeah, what else might be out there is a wonderful question. And it's-
Further questions? Any further questions?
So imagine I'm Elon Musk listening to this, and I'm concerned about all the money we're spending. And you're answering questions or beginning to speculate on answers of questions that will matter to us as human beings in billions of years.
yes. So Elon Musk,
Wouldn't it make sense right now for us to be spending money on psychology and
Yes.
psychiatry rather than on
let me
these
rephrase
advanced?
your question. How should we cut up the pie available for research? I think that's what you're really asking. And doesn't too much money go into astronomy and not enough into psychology? So I hate to say it, but the reason we have politicians is to make funding decisions. And look at the politicians like Musk that we're going to have for the next 4 years. It's frightening. It's frightening. There'll be no money. It's not just a matter of priorities.
Any further?
What would we lose if we stopped all the money that's going into this?
I can't answer that. Humans have curiosity, and astronomy has been fairly well funded through all kinds of different funding crises, and it's just because we want to know these things. I think the astronomy budget will survive. I'm a lot more concerned about chemistry and theoretical chemistry as opposed to applied chemistry, which builds products that sell. I think they're, especially in the social sciences, they're in for a very rocky time. This has happened periodically. You've lived through this before.
On behalf of the entire group, I want to thank you, Dr. Baker,
you're
for
quite welcome.
a very exciting and stimulating lecture. And all of the long-term news is really grim. The good news is we're not going to live to see it. So
That's right. Enjoy yourself while you can.
they say if you book passage on the Titanic, go first class.
Well said.